For our final project, we decided to create an AI model to play the classic Snake game for us. Our group consists of me, Ammar, Lauren, Eralp, Johanna, Alan, and Daniel. The video game Snake has been around for decades, giving people plenty of time to hone their skills. However, we wanted to see if a human player can be surpassed by AI. Many data scientists have experimented with AI video game players, which can be seen in famous games such as Dota and Go. Our main goal is to create an AI model that learns to play Snake better than a human could. The motivation for our SnakeAI project is simple: to explore reinforcement learning and use its application in a way that is interesting to us and very intuitive to understand. The choice of the Snake game was perfect for our final project because it had just the right amount of complexity needed to explore reinforcement learning while maintaining the level of simplicity needed for implementation purposes. Additionally, video games tend to be a natural application of reinforcement learning, making them a good starting point for exploration. We also got the experience of building a classic game as we chose to build the game ourselves. So first we need to begin by defining what it means to be a better player. We need to consider the trade-offs between highest score and game time. An algorithm to obtain the highest score could certainly be found in any game of Snake using Hamiltonian cycles, but this takes away much of the spontaneity a human player would use in their games. Hamiltonian cycles traverse each node, in our case, are the coordinates on the map, once and have the same starting and end point. So as you can see on the picture, they start and end in a pretty simple fashion. So this path would be safe and would be slow to obtain the optimal score, which would occur when the snake is too long and takes up every block on the screen. However, the food pellets spawn at random points across the screen, and the pellet's location is not taken into account in this algorithm. Also, constantly following a set path would be boring to watch, and movements would be feeling very robotic. A smart AI, while not perfect performer, would be faster and more interesting to watch.
To train our model, we first needed to create the environment, the Snake game itself. We implemented this in Python using the Pygame library, allowing configurations for either player input or computer controls. The basics of the game are the same as any Snake game. The snake can travel forward, left, or right at any time. It gains points by moving its head on top of the food that spawns at random locations on the map. After eating the food, the snake's body grows, providing the player with an increasingly difficult obstacle as the game progresses. The game ends when the snakehead hits the boundaries or its own body. By creating our implementation of Snake, we are provided full control of the features. Most importantly, we can create an API for our AI to control the snake and receive any necessary data about the current state of the game, such as the snake's relative position to dangers or food. After creating the game and AI, we noticed some strange AI snake behaviors and changed the game to fix them. In particular, the snake had a strong tendency to travel in certain directions during early training. This was because spawning position and direction of the snake, as well as the position of the first food, which was hard-coded, not random. After randomizing the spawning state of the game, the AI snake performed much better. Using our custom game API, we created an agent to interact with this snake environment. In every game cycle, the agent evaluated its input data, the state of adjacent tiles, and if they are safe or dangerous, their current direction, and the relative direction of the food. Based on this information, it outputs an action for the snake to take, forward, left, or right. The fourth option of going backwards is not programmed into the agent because the game does not allow the snake to go backward. The selection process is decided by our model, as detailed previously, in which previous moves and games reinforce the proper behavior for our agent. We implemented this in both Q-learning and deep Q-learning. These are some of the parameters we took in order for our agent to make the right decisions.
To train our AI, we heavily utilized reinforcement learning and its associated concepts when implementing our model. By using reinforcement learning, a type of machine learning training method based on rewarding desired behaviors and punishing undesired ones, we were able to create an agent that would learn how to play the game of Snake similar to how a human would, through trial and error. It is important to note that this type of machine learning differs from supervised learning which predicts the optimal output using past data, and unsupervised learning, which is used to identify important clusters in data. The basic elements of a reinforcement learning problem include its environment, state, reward, policy, and value. On the next slide, we have our specific type of model, which is Q-learning. And the benefits of using this technique is that it's very straightforward to understand and intuitive to use. Given its current state, Q-learning aims to find the best or highest quality action. By training our model, we are able to determine the action that will maximize the future reward given the current state. Q-learning uses a Q table to map specific state action pairs to a Q value, which is the maximum expected reward the AI can reach by taking a given action from the specific state. Initially, all values in the Q table are set to 0 because the AI knows nothing about its environment. Because of that, the AI starts doing random moves to explore the world. Through these random moves, the AI learns each state action pair's expected rewards and updates the Q table with a new calculated Q value using the Bellman equation listed below, which is actually on 2 more slides later. There are many ways to tackle this trade-off between exploration and exploitation, and we use the most commonly solution called epsilon greedy exploration strategy. And with this strategy, we have an epsilon value, which is initialized to a certain value. And this is used for our SnakeAI to determine whether to follow its current policy or select a random action. With more experience in development, the AI decrements this same epsilon value with a custom rule. In other words, when it becomes more knowledgeable, it exploits its current policy, exploits its current Q value, and explores less as it goes on. The chosen action made by the AI necessitates a reward, and the Q values and the Q table are correspondingly updated. And again, this is updated by the same Bellman equation. However, there is a drawback to the Q-learning algorithm, and for this, I'm going to hand it over to Johanna.
So for the implementation of our regular Q-learning algorithm, we kept a Q table in our memory, and this took the inputs of like state and action combinations and kept the Q values for each action. So after every step of the game, the regular Q-learning uses the update rule to store a new Q value based on the outcome of the completed step. The table also occasionally updates based on the sample of previous turns. So our agent can then compare the 3 action Q values to decide the best move. The drawback to the Q-learning algorithm, as with the table, is that if we want more inputs for each current state to improve the agent's performance, we have to increase the size of the Q table, which increases memory usage. The number of entries in the Q table is 2 to the power of the number of state variables times the number of actions per state. So the complexity is really in the order of 2 to the n. As a result of that, we also used deep Q-learning, which addresses this high memory issue.
So the deep Q-learning algorithm extends standard Q-learning by using a neural network to evaluate the Q value. Instead of storing each action pair in a Q table as seen in standard Q-learning, the deep Q-learning architecture stores discovered state data in a smaller table known as the replay buffer. A random batch of data is sampled from the replay buffer and is used for training the neural network. As shown in the figure on the right, the neural network contains a linear input layer that takes state as an input, any number of intermediate hidden layers, and a linear output layer that outputs the Q value of each action. Just like the standard Q-learning algorithm, deep Q-learning commonly uses the epsilon greedy exploration strategy to choose between making a random move called exploring or the move that gives the highest expected future reward called exploiting. If the randomly generated number is greater than epsilon, then the AI will look at the output layer of the neural network and pick the action with the highest Q value. Once the action is performed and the reward is measured, the system then stores this new state data into the replay buffer, where a random batch is selected to calculate the new Q value using the Bellman equation. Finally, the neural network is trained to minimize its selected loss function. These steps are then repeated for a chosen number of times. In many ways, Deep Q learning is better and more applicable than standard Q learning. Most importantly, deep Q learning can handle large states and action spaces. Increasing the number of states and action spaces does not increase the memory of the replay buffer. Secondly, deep Q learning can handle continuous inputs for the states because any real number can be used as inputs to the neural network. Standard Q learning, however, uses binary inputs for the Q table, which does not work when a state has a continuous value. On the other hand, deep Q learning is slower than standard Q learning because the neural network has to be trained after each Q value update. In our deep Q learning implementation, we train a neural network every game cycle using the current game state and action, as well as saving the current game state and action into memory. After every game finishes, the model is retrained with a random batch of previous game data. Our neural network was implemented using PyTorch. Its architecture was simply composed of 2 linear layers with an intermediate hidden size of 256 neurons.
So as for our results, we trained our game over 1,000 times, each on different grid size to evaluate the performance of the model. We did better on the 6x6 using deep Q learning, but we did worse on the 32x32. So what we found was that as the map grows, the snake's routes needed to be smarter and navigate around the growing body to be successful becomes harder. However, the model doesn't have enough inputs to avoid trapping itself within its body. So that's why the results get worse as we progress in the grid size. And then sometimes when training, the snake just happens to be unlucky because it may be difficult to eat the food, which when randomly navigating through the entire map. It's necessary for the snake to eat the food to help reinforce his behavior. However, if the snake does not encounter the food in the early stages of learning, this behavior may not be reinforced and the snake may lean towards other behaviors such as circling around the border. This is called a sparse reward problem. This issue could be solved by starting with a large amount of food on the map during the early stages of the exploration and then slowly decreasing the amount of food on the map until there's only one left.
So there are many improvements we could have experimented with and implemented to improve the performance of the SnakeAI. So first of all, instead of providing the agent with just the relative direction of the food, we could have instead provided the agent with a numerical distance of the food in each direction. However, this would only be practical with a deep Q learning network, as this would require too much storage in standard Q learning due to the continuous variables. In addition, we could provide the agent with more information regarding dangers in its surroundings. Instead of only providing safety data of the 3 adjacent squares, we could expand the vision around the snake's head so the agent would be able to see more obstacles around itself. This extended vision would assist the agent in some simpler situations where the snake is about to trap itself. However, the snake would require vision of the entire map to have the ability to never trap itself and win consistently. There are also alternative models and reinforcement learning approaches that could be experimented with. For example, double deep Q learning is an interesting approach that shows promise. Double deep Q learning solves the issue of overestimation with regular deep Q learning. Also, data scientists online have reported success with the actor-critic model, which improves the exploration aspect of Q learning. In Q learning, the exploration is done by choosing a completely random direction. However, the actor-critic model provides an estimated distribution of success between the 3 possible actions, and exploration is done by sampling within this distribution. This helps solve the issue of prematurely ending the game due to selecting an obviously bad random action, such as running into the wall. So in this project, we explored and implemented a regular and deep Q learning AI for improving performance in the game Snake. Both of our Q learning implementations performed similarly. This leads us to the conclusion that deep Q learning is the better approach for a Snake AI because it requires significantly less memory while maintaining similar performance. While the AI Snake score performance was nowhere close to perfect, it acted interestingly and human-like and performed well enough for us to consider this implementation a success. On average, the Snake performed better in terms of score in comparison to our human team, which was our goal.